Hey guys, welcome to another episode of Kitchen Table Chemistry. It is Tuesday, April 14th, and in today's edition of Kitchen Table Chemistry, we are going to talk about the ideal gas law. The ideal gas law is a law that governs how gases behave and will allow us to look at finally moles of a gas. So the ideal gas law is different in that we'll now be considering moles of a gas in only one set of conditions. The reason why I have helium up here is because helium is the most ideal gas. And what is it that makes a gas ideal? Well, what makes a gas ideal is this. It should have no mass or as close to no mass as possible. Helium is, of course, a great example of this because it has very, very little mass. Heavier gases, something like sulfur hexafluoride, SF6, have a lot of mass and don't behave as ideally. An ideal gas would never condense into a liquid. It would stay a gas no matter what the pressure ever. So it's a little bit unrealistic that way, but most gases will behave under normal conditions like an ideal gas. An ideal gas will have no attraction between the particles. The particles will be right next to each other and not be attracted to each other. This again would explain why it never condenses into a liquid. Again, helium is a great example of this because of its electron structure. It's very, very little attraction to other helium particles. An ideal gas, the particles would take up no space. In other words, they would be dimensionless. So because they would take up no space, you could go down to a zero temperature, zero mass type situation. And again, the most ideal gas is helium because it is the closest to all of these things. Okay, the ideal gas law. Oh, and that's why. So what it does, I'll just put myself up here. Helium, because very, very small size, very, very small particles, small mass, and that little attraction, helium is the most ideal of the gases. As a matter of fact, the noble gases are the most ideal acting of the gases. Now, next. The ideal gas allows us to look at moles of a gas. We're only going to have one set of conditions. This is going to be different, just one set of conditions, and that one set of conditions will be changing or working with. And our pressure here has to be either in kilopascals or ATMs. We're never going to work with millimeters of mercury with this. Volume has to be in liter and temperature has to be in Kelvin. So units are going to play a bigger part in this. And then again, we're going to be able to look at moles. There's going to be an R in this. R is the ideal gas law constant. And what's coming up, I want you to put on the back of your periodic table. It's always going to be available to you. You need to get comfortable working with it and what it is. It is a constant. So R is 8.31 liters times kilopascals over moles times K. Notice that pressure here is in kilopascals. There's 4 units, liters times kilopascals over moles times Kelvin. R can also be liters times atmospheres over moles times Kelvin. So why give you 2? Because sometimes you're going to be in kilopascals, sometimes you're going to be in atmospheres. You may as well have both. That way you can use either one and you don't have to waste time going between the two. Okay, next. The ideal gas law is written up here at the top. PV is equal to nRT. Pressure times volume is equal to moles of a gas times the gas law constant times temperature Kelvin. This here is the crux of the matter and what we'll be working with today. Secondly, it can be PM equals DRT. This large M here is going to be molecular mass or gram formula mass. D here is going to be density. And then finally, PV equals small m RT over large M. This M here is simply mass in grams. And this here is, again, the formula weight or gram formula mass. So different ways of looking at the ideal gas law. We're only going to be doing the top one today. Now, here's an example. What is the volume of 0.75 moles of hydrogen? So I know what my moles are. They're 0.75 moles at 130 kilopascals. So that's my pressure. And that 130.0 kPa tells me which R I'm going to use. So I'm going to be using 8.31 liters times kilopascals over moles times Kelvin. And again, the R will be dictated by your pressure unit. 25 degrees Celsius, and immediately need to put that into Kelvin, so 298 Kelvin. And our volume here is the X that we're going to try to find. So PV equals nRT, so we'll set this up. P times V is equal to number of moles times the constant times the temperature. The pressure then, 130.0 kPa, times the volume I don't know, is equal to the moles here, 0.75 moles, times R, which is 8.31 liters times kilopascals over moles times Kelvin, times T, which is 298 Kelvin. Now notice initially here, moles and Kelvin are going to cross off like that. And it's going to leave us in liters times kilopascals. So volume then is going to equal 0.75 times 8.31 liters times kilopascals, that I'm now going to divide by 130.0 kPa. So now the kPa's will cross out. The only unit left is liters, and I get a final volume here. I got 14, and I'm going to go 14.0 liters. We're going to go to 3 sig figs on this one. 14 would be a good answer. So our volume is equal to 14. I'm just going to go with a decimal point liters. And notice that's not V1 or V2. It is the only volume. So this is how you solve a ideal gas law problem and set up. I think it's pretty straightforward. I'm going to give you some straightforward, easy examples to work on. And then through the week, we'll be adding some different levels and difficulty as we go. Tomorrow is going to be a quiz on everything up to the combined gas law. It'll be a Google quiz. I'll put on the instructions for that when you get it. So be interested and ready to go with that when it arrives tomorrow. Very small assignment today, just to do some practice with this stuff as we get our feet wet with the ideal gas law. Take care, and I will talk to you. Bye-bye now.